Today we're covering section 4-4. If you haven't got your term sheets yet, please make sure you do that. We want to talk first about complex zeros. We've already talked about the real zeros of polynomials. We're going to talk about complex zeros today. And the first thing we want to talk about is the fundamental theorem. Every polynomial, p of x, and again we've seen this form before. This is just standard form of any polynomial where n is greater than or equal to 1. That's the degree of the polynomial, and then the leading coefficient is not 0. So every polynomial of that form with complex coefficients has at least one complex zero. The complete factorization theorem says if p of x is a polynomial with a degree greater than 0, then there exist complex numbers a, c1, c2, and then all the way up to cn, again with a not equal to 0, such that p of x can be factored as you see there, a times x minus c1 times x minus c2, and then all the way to x minus c sub n. These are two important theorems that help us know how we can factor polynomials when we are allowed to use complex numbers. We're going to look at a couple of examples of how to factor, and I'll be showing you those shortly. You can see both of those. P of x equals x cubed minus 3x squared plus x minus 3 in example 1. And in example 2, p of x equals x cubed minus 2x plus 4. And we will factor each of those completely using complex numbers, which will mean that we're going to have to use the quadratic formula to solve it once we get it down to being a quadratic. In example 1, we're going to factor this polynomial, and we're going to factor it completely, which means we're going to factor it all the way down to complex numbers. And as we look at this, the first thing that you might notice is that there are 4 terms. And if you remember, we've done some factoring before with 4 terms, and we factor by grouping it. And actually, if you look at this pattern with a 1 and a negative 3 as the coefficient here, and another 1 and a negative 3 as the coefficient there, that's going to factor very nicely for us using grouping. So let's go ahead and do that. We'll factor by grouping, and we can take out an x squared from the first terms, the first group, and what's left there is x minus 3 plus, and we can't take anything out of the second group, so we have x minus 3. And so that means we're going to have x squared plus, there's automatically a 1 in front of there, and then here we have x minus 3. Now to finish this off, what we actually are going to go ahead and do is find the 0 of this one, the zeros. So if we think about that, x squared plus 1 equals 0. If we solve that, we subtract 1. So x squared equals negative 1. And therefore, when we take the square root of both sides, we get x equals plus or minus I. Now if these are the zeros, remember the factors are going to be x plus I and x minus I, and that also will go with the x minus 3. So our complete factorization of p of x here is x plus I times x minus I times x minus 3. So that is example 1. And if you didn't see the factoring by grouping, we can always go back and use the rational zero theorem, which we are going to use here throughout the rest of the day. But we could have found those zeros plus or minus 1 and plus or minus 3 would be the numerator values that we have to use, and then just 1 is the denominator. So you can see the one that would have worked would have been a positive 3 when we checked that one out. So that is example 1. Great. Okay, example 2, we're factoring again, and this one is a little bit trickier because it's not a nice grouping problem. But we can look at the possible rational zeros. Remember, we take the factors of 4, which are 1, 2, and 4, and that's plus or minus for each of those. And those are the numbers that can be on the top, and then the factors of the leading coefficient, which is 1, those are the numbers that can be on the bottom. So as we look at this, again, I always like to start with 1, but for the sake of time, there's only 6 here to check, and I'm just going to tell us that the one that's going to work here is actually negative 2. So just to save a little time in the example, we see the process. Remember, we're going to have the leading the coefficients 1, we need a 0 for x squared and a negative 2 and a 4. So when we divide that, we've got the 1 coming down. 1 times negative 2 is negative 2. So we add those. Negative 2 times negative 2 is 4. We add those, and that gives us a 2. 2 times negative 2 is negative 4, and that gives us a 0. So negative 2 is one of our zeros. Then what we have left is, remember this was cubic, so this is now x squared minus 2x plus 2. And we're going to find the zeros of that using the quadratic formula. So again, a is 1, b is negative 2, and c is 2 from 1, negative 2, and 2 from our standard form. So let's use the quadratic formula here. X equals the opposite of b, so we get that plus or minus the square root of b squared, so negative 2 squared minus 4 times a, which is 1, times c, which is 2, over 2 times a. And as we continue simplifying, we get 2 plus or minus 4 minus 8 over 2, which is 2 plus or minus the square root of negative 4 over 2. Now remember, this negative means we take that out and it becomes an I, because that's the square root of negative 1. And then what we have left is 2, and when we have an I, we're going to split these up. So 2 over 2 plus or minus the square root of 4 is 2 over 2. So that gives us 1 plus or minus, those cancel to a 1 also, we get 1 plus or minus I. So the zeros are negative 2 and 1 plus I and 1 minus I, but we were asked to find the factors. So our factors are x plus 2, x minus 1 plus I, and x minus 1 minus I. And so that is our factorization in this case for p of x. But again, the process is, if you're not sure, find the rational zeros, check which ones work using synthetic division right here. And then once you get it down to a quadratic, you can also always use the quadratic formula. We have talked about multiplicity before, and here's a statement applying to that. If the factor x minus c appears k times in the complete factorization of p of x, then we say that c is a 0, and then that 0 has a multiplicity of k. So for instance, if x minus 3 occurs in a factorization 5 times, the 0, x equals 3, has a multiplicity of 5. And we'll see some examples of that. The zeros theorem says that every polynomial with a degree greater than or equal to 1 has exactly n zeros. So if n is the degree, it has to have n zeros, as long as, or provided that, a 0 of multiplicity k is counted k times. So for instance, if your multiplicity is, if your degree of the polynomial is 7, there will be 7 complex zeros, as long as you count the multiplicities. In example 3, we're going to factor this polynomial completely. In example 3, once again, we're factoring completely, but we will notice that in this case, we can actually factor out a 3x from each of those terms, and what we have left is x to the 4th plus 8x squared plus 16. And in this case, notice this has a quadratic pattern, even though it's really a degree of 4. So we've got a quadratic pattern here because this degree is twice as much as this one. And that's anytime you have that pattern where this degree is twice as much as this one, that exponent, you've got a quadratic pattern. So what we can do is we can factor this using the methods that we've used before with quadratics. The difference is this is going to be x squared and this is going to be x squared instead of them just being x's. So then we look at this and we find out the signs are the same and they're both positive. So we want factors of 16 that add up to be 8, and those factors would both be 4. Okay, but if we're going to factor over the complex numbers, we're not going to have any x squareds left. So let's take one of these. set it equal to 0 to find those zeros. So we subtract 4 and take the square root of both sides, and we find out that x equals plus or minus, and again we had this one in the last example, this is 2i. So that means when we factor it completely, we have the 3x from right here, then we have x plus 2i and x minus 2i from here. But notice this factor is exactly the same, so each of these actually happens 2 times. So we can put 3x times x plus 2i squared, and then times x minus 2i also squared. So that's where we get our answer on example 3. And we can see here that each of these has a multiplicity of 2, the 2 complex factors. Looking at examples 4 and 5, here we are going to kind of go the other direction, where we're starting with the zeros and we're going to find a polynomial that fits this information. And we're going to do that for example 4 and for example 5. In example 4, we're asked to find a polynomial with a degree of 4 with the following zeros: I, negative I, 2, and negative 2. So basically this just boils down to multiplying this out. X minus I, x plus I, x minus 2, and x plus 2. Now we do have one additional condition at the end, and we'll look at that in a little bit. So what I always do, and this is what you should always do, always multiply the I ones first. So when we FOIL that, we get x squared plus ix minus ix minus I squared. And then when we multiply the other ones, you've got x squared, same pattern, plus 2x minus 2x and minus 4. So this, notice these cancel out and these cancel out. And remember that I squared is equal to negative 1. So we've got minus negative 1 here. This becomes x squared plus 1 times x squared minus 4. So when we multiply this, again foiling it, we get x squared minus 4x squared plus 1x squared minus 4. And that gives us, sorry, this is not right, x to the 4th should be here, x squared times x squared. That gives us x to the 4th minus 3x squared minus 4. Now, this polynomial right here would have these 4 zeros. But the additional condition we were given is that p of 3 equals 25. So what happens is, to adjust this, that whole polynomial with those zeros can be multiplied by any scalar, and we'll call that scalar a. And a scalar is just a number. So what we want to do is we want to plug in this value. P of 3 is going to be 25, which means in place of all those x's, we're going to put in 3's. So 3 to the 4th power minus 3 times 3 squared minus 4. And we're trying to figure out what a is, and then we'll just plug that back in. So 25 equals a times 81 minus 27 minus 4, and that is 25 equaling a times 50. And then we divide both sides by 50, and we get a equals 1/2. So if we plug that in right here, 1/2 times x to the 4th minus 3x squared minus 4, we are going to get our final polynomial, p of x equals, distributing 1/2 x to the 4th minus 3/2, 1/2 times 3, x squared, minus, and then 1/2 times 4 is 2. So there is our final polynomial after we get those zeros and also the condition that p of 3 has to equal 25. In example 5, once again, we're finding a polynomial given certain zeros, only this time the twist is they're saying that negative 2 has a multiplicity of 3. So that 0 occurs 3 times. So then our factors are x minus 0 if you want to write it, but you don't need it. X plus 2, x plus 2 again, and x plus 2 a third time. Notice this time we're not given that additional condition of having to put it in exactly one spot. So We're just going to multiply this out. We've got x. We're going to FOIL this. We get x squared plus 2x plus 2x plus 4. And that's x plus 2. This simplifies to be x squared plus 4x plus 4 times x plus 2. And we have to distribute this again. So x stays there. X squared times x is x cubed. X squared times 2 is 2x squared. 4x times x is 4x squared. 4x times 2 is 8x. And then finally 4 times x. And 4 times 2. So again, simplifying that a little bit, these things are all equal from the very beginning. We've got x cubed plus 6x squared plus 12x plus 8. And then our final step is just distribute the x. So x to the 4th plus 6x cubed plus 12x squared plus 8x is the polynomial that we find that has 0 and negative 2 as the zeros, and negative 2 has a multiplicity of 3. In example 6, we're back to finding all the zeros. So we're going to try and use synthetic division to factor this, or to find the zeros of this, and then get it completely factored, or finding all the zeros. In example 6, we're finding the zeros. So again, our goal is to figure out what rational zeros may work. So as we look at that again, we take the factors of 4, which are plus or minus 1, plus or minus 2, and plus or minus 4, only this time we have on the bottom factors of 3, so 1 and 3. So our factors that we could have, plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 1/3, plus or minus 2/3, plus or minus 4/3. And those are the 12 possible rational zeros that we're going to have to look at. As we look at this, again, for the sake of time, we've got 12 to check. One thing we might want to look at is our Descartes' rule of signs. And if we look at this, we can see that this is a positive. It switches to a negative coefficient, stays negative, stays negative, stays negative. So we know there's at least one positive zero. And in this case, I'm going to go ahead and figure out which that one is a 2. So let's go ahead and check 2. Again, for the sake of time, we've got these coefficients to use in our synthetic division. So we get 3 and 6, 4, 8, 7, 14, 2, 4, and 0. So remember, this was x to the 4th. This is now x cubed. Now, one thing that's nice is when we're looking at these zeros, the constant is now a 2, and the leading coefficient is now a 3, which means 4 can't be a 0 of this because the factors here are now factors of 2 on the top. So we break it down to that, and also 4/3 cannot be a 0. So now we have only 8 left to look at again, and we found the positive one. So since there was only one positive one using Descartes' rule of signs, the others have to be negative or imaginary. And we are going to check some of these imaginary ones. And again, for the sake of time, we'll check negative 1/2 is going to work for us. Oh, I'm sorry, not negative 1/2, negative 1/3 is going to work for us. So let's go ahead and do that. So we bring this down, we get a 3. 3 times negative 1/3 is negative 1. That gives us a 3. We'll get a negative 1 again. That gives us a 6. 6 times negative 1/3 is negative 2. And that gives us 0. So now, if we look at what's left here, we have 3 times x squared plus 3 times x plus 6 equals 0. So here's one 0, here's another 0. As we look at this, we're going to go ahead and use the quadratic formula, but before we do, notice all of these are divisible by 3, so let's just divide everything by 3, and that gives us x squared plus x plus 2 equals 0, and that's what we'll use in our quadratic formula. So, we've got x equals negative b, which is 1, plus or minus the square root of b squared, that's 1 squared, minus 4 times 1 times 2, because the c value is 2, over 2 times a, which is 1. So again, continuing to simplify, negative 1 plus or minus 1 minus 8 over 2. And that gives us negative 1 plus or minus the square root of negative 7 over 2. Again, that negative comes out as an I. We can't break up the 7. So our other zeros here, we want to split this up. X equals negative 1/2 plus or minus the square root of 7 over 2 times I. So notice here are the 4 zeros. 2, negative 1/3, and negative 1/2 plus square root of 7 over 2I, negative 1/2 minus square root of 7 over 2I. That gives us 4 zeros. Okay, the conjugate zeros theorem is another important one for us, and it says that if a polynomial p has real coefficients and if a complex number is a zero of p, then its complex conjugate is also a zero of p. And we've talked about conjugates before. If you look actually up at this answer right here, negative 1/2 plus square root of 7 over 2 times I, and negative 1/2 minus square root of 7 over 2 times I. Those numbers, if you remember, are called conjugates because this sign, the numbers are identical except for this sign and this sign have just been switched. In one it's a positive and in one it's a negative. In example 7, we find a polynomial of degree 3 with integer coefficients, and the zeros are 1/2 and 3 minus 1. And then example 8, find the possible number of each type of zero using Descartes' rule of signs. So we're finding the positives, we're finding the negatives, and then we'll also look at how many could be imaginary. In example 7, we're finding a polynomial of degree 3 with these zeros. Notice we've got x minus 1/2, and this one gives us x minus 3 plus I. But remember that if this is a zero, we have another zero that has to be there because of that conjugate theorem, and it's that one. So that gives us this zero, x minus 3 minus I. And so we want to multiply these out. Again, multiply the imaginary ones first. So x minus 1/2 stays here. And actually what we're going to do, because we're supposed to have integer coefficients, we're going to multiply this first one by 2. So that gives us 2x minus 1. Notice that gives us the same zero if we solve it. And this we're going to multiply out. X times x is x squared. X times negative 3 is negative 3x. And then we get minus ix. And then negative 3x again. Plus 9. Plus 3I. Plus ix. Minus 3I. And finally minus I squared. Now notice the ix's cancel and the 3i's cancel, and remember, subtracting an I squared, that really means plus 1 because you're subtracting a negative 1. So now we have 2x minus 1 times x squared minus 6x plus 10, and then to multiply that out, 2x times x squared is 2x cubed minus 12x plus 20x minus x squared plus 6x minus 10. So 2x cubed, wait, I've got something wrong here, I think. 2x times 6x should be 12x squared. So negative 12x squared would be minus 13x squared plus 26x minus 10, and that is our polynomial that has those zeros. And it's, notice it is third degree. So 2x cubed minus 13x squared plus 26x minus 10. If you remember Descartes' rule of signs, it tells us how we can figure out the number of possible positive solutions or negative solutions. So to look at the number of positives, we check P of x, and we look at the coefficients. Notice this coefficient is a positive 1, this one's a positive 6, negative 12, negative 14, negative 24. And we count how many times these coefficients change from a positive to negative or back. So notice it's a positive, it stays positive. That's one change. And then notice the rest are negative. So there is one, if we write it down here, positive, there's one positive solution, no matter what. There has to be one positive. To check the negatives, we have to check out P of negative x, which is negative x to the fourth plus 6 times negative x cubed minus 16 times negative x squared minus 14 times negative x minus 24. That gives us x to the fourth minus 6x cubed minus 12x squared plus 14x minus 24. So notice that's positive, negative, negative, positive, negative. So we've got one change, two changes, three changes. So the most negative solutions we could have is we could have 3. Or remember, we can always go down by an even number. So we could also have 1. And notice that no matter if there's 3 negatives or 1 negative, there has to be one positive, always. Now, the other part, and the reason we have this going down by 2s, is the whole deal with imaginaries. And if there is 1 positive and 3 negatives, and the degree is 4, and there has to be 4 solutions, that means there can't be any imaginaries. But since we know that imaginary answers come in pairs, conjugate pairs, if there was any imaginaries, there would have to be 2. And that's why when we go down, we always go down by 2s, or an even number, because any imaginary numbers always have to come in a pair. And so that means there's always an even number of imaginary solutions. So as far as positives, there has to be 1 no matter what. So like case 1 would be 1 positive, 3 negatives, and no imaginaries. Case 2 would be that the other possibility would be there's 1 positive, 1 negative, and 2 imaginaries. So that's example 8 using Descartes' rule of signs. The linear quadratic factors theorem: every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. That term irreducible means exactly what it does when we're talking about numbers. It means we can't divide anything into that evenly. So there's no other polynomial. If we're talking about irreducible quadratic factors, there's no other polynomial that will divide into that quadratic evenly. So in example 9, we're going to factor the following polynomial into irreducible linear and quadratic factors, and then we will factor it completely using the quadratic formula after we do part A. In example 9, we're supposed to factor in part A with linear or irreducible quadratics, and in part B factor completely. Notice this again is that quadratic form where this exponent is twice as much as that one, so we can actually just factor this one using parentheses, x squared and x squared. The signs are different, one's positive, one's negative, and it's going to be a negative 4 and a positive 2. Well, this one we can't factor anymore. It's irreducible over the real numbers. But this one, notice, is the difference of 2 squares because it's subtraction. So x squared plus 2. This one is x minus 2 times x plus 2. So that would be part A, where we're factoring to linear or irreducible quadratics. To finish this one out, the easiest way is just find the zeros. Or if you have to, use a quadratic formula. We get x squared equals negative 2. Square root of both sides, we get x equals plus or minus the square root of 2 times I with that negative. So that means this part factors into x minus I square root of 2 and x plus I square root of 2. And these other two factors, x minus 2 and x plus 2, just stay. So notice when we're all done, linear factors, we've got 4 of them because the original degree was 4. So this is factoring over irreducible quadratics and linear, and this one is factoring it completely into linear using complex numbers. Again, this is a suggested assignment. Take a look at section 4.4, page 354 and 355. We will have a workday tomorrow. We will finish up the end of section 4.3, which we actually have not finished yet, but I didn't want to make the sub try and do that. So we'll be covering that tomorrow, and I will also answer any questions that you have on section 4.4 after watching the video. Have a good afternoon, and again, congratulations to the Cubs for their victory last night.